In January 2026, NASA confirmed something that should not have been there. A galaxy sitting only 280 million years on the far side of the Big Bang, brighter, denser, and more chemically mature than any theoretical model had ever allowed for. The researchers who pinned it down admitted it openly. It did not resemble what anyone had prepared themselves to find. That same year, the sharpest standoff in contemporary cosmology crossed the statistical threshold that physicists reserve for formal discovery. Two independent methods of gauging how quickly space is stretching are returning two irreconcilable answers. The gap between them is no longer a curiosity. It is not a discrepancy waiting to be cleaned up. It has become a crisis. The framework we have used to interpret the cosmos for a quarter of a century may be fracturing. And if it is fracturing, then every confident number we have ever published about how large the universe really is, how it assembled itself, and what substance lies underneath its surface, is suddenly open for renegotiation. Tonight, we are going to walk from the thin crust of this small planet all the way out to the boundary where light itself surrenders. We are going to discover that 80% of the cosmos is essentially vacant. We are going to find that 95% of reality is composed of ingredients we have never once laid hands on and do not understand at even a conceptual level. We are going to step inside an emptiness 330 million light-years wide that contains almost nothing worth describing. We are going to look at the very first photograph ever taken of the cosmic web, the single largest object in existence. And we are going to sit with the possibility that the observable universe, the full 93 billion light-year sphere we have spent centuries charting, is nothing more than a peephole, and the chamber on the far side of it could be 100 trillion times larger. By the time we arrive at the end of this journey, you will understand why the question of whether we are alone may have nothing to do with biology at all. It may turn out to be a question about geometry, about construction. The universe may have been laid out in such a way that any two thinking beings inside it are permanently kept at arm's length from each other. If you enjoy these long nocturnal excursions through the cosmos, please tap the like button and subscribe so the channel keeps growing. We strongly encourage everyone in this community to share their reactions below and to respond to the comments of others. These videos are always best when the conversation keeps moving afterward. And if you find that your memory has been slipping, or that you simply want to sharpen it, take a look at our affiliate partner, The Brain Song. It is a daily 12-minute audio routine grounded in neuroscience, designed to help your mind retain and recall information more efficiently. You can read more about it in the description below this video. Now let us begin. Tonight, we are going to take you somewhere that will leave you feeling unnervingly small. Not small the way you feel when you crane your neck at the foot of a mountain. Not small the way you feel when a thunderhead rolls over an empty prairie. Small in a way your nervous system was simply never calibrated to absorb. Because tonight, we are going to measure the cosmos itself. And what we are going to uncover is that almost every instinct you carry about how large it is, how it functions, and what substances fill it is either badly incomplete or simply wrong in a foundational way. Over the next couple of hours, we will walk from the thin shell of our small blue planet all the way outward to the limit of everything light has ever had a chance to visit. We will learn that 80% of the universe is hollow. That 95% of existence is constructed from ingredients we have never identified with a single direct detection. We will discover that the largest structure in the known cosmos was photographed for the first time in human history only last year. A corridor of gas and dark matter stretching 3 million light-years across between two ancient galactic cores. We will face down the deepest crisis modern cosmology has ever produced. A straightforward disagreement about the most elementary property of the universe, namely how fast it is swelling, that has now passed the statistical bar physicists use to certify a discovery as real. We will meet a galaxy that should not have been permitted to exist. A galaxy that ignited only 280 million years after the Big Bang, far brighter and more organized than any model could accommodate. A galaxy the lead scientists confessed looks nothing like anything we had prepared ourselves to see. And at the end, we will ask the oldest question human beings have ever asked. Are we alone in all of this? but by the time we arrive there, you will understand that question very differently than you do right now. Because the answer may not be about biology at all. It may be about the floor plan of reality itself. The universe may not simply be too large for us to find a neighbor. It may have been engineered, in the physical sense of the word, to keep every conscious being permanently separated from every other. Chapter 1. The sky is telling you a lie. Step outside tonight. Find a corner of the world where the street lamps cannot reach you if you can manage it. Tilt your head back, let your pupils widen for a few minutes. After a while, thousands of faint points of light will emerge across the blackness above you. On a genuinely dark night, far from any settlement, you might be able to pick out around 4,000 of them at once. The sight feels limitless. It feels as though you are staring at the universe in its entirety, unfurled like a banner across your field of vision. You are not. Nearly every star you are able to resolve with your unaided eye sits within roughly 1,000 light-years of the surface of the Earth. That sounds vast, 1,000 light-years. But the Milky Way galaxy, the island we inhabit, spans 100,000 light-years from edge to edge. That means your nightly view covers about 1% of the width of your own galaxy. And that tiny sliver contains almost nothing when you compare it to everything that lies outside it. The Milky Way is believed to hold around 250 billion stars. You can see 4,000 of them at most. That is like standing on a sidewalk in Manhattan, identifying one single building in the distance, and calling that the skyline of the city. Now take a step back further. The Milky Way is a single galaxy. The observable universe contains an estimated 2 trillion galaxies. Each one of them holds billions or hundreds of billions of stars. The grand total of stars in the observable universe clocks in around 10 to the power of 24. A 1 followed by 24 zeros. There are more stars in the observable universe than there are grains of sand on every beach and in every desert on this planet put together. And every flicker of light you have ever noticed when you looked upward after dark is a microscopic chip off one of those 2 trillion galaxies. The night sky is not a window onto the universe. It is a keyhole. And what you catch a glimpse of through it is nothing more than the neighborhood you happen to live on. The actual cosmos is vastly, incomprehensibly larger than anything your eyes are communicating to your brain. And here is the part that truly disturbs the professionals. Even the scientists who have spent their entire careers studying the universe are beginning to suspect that their own picture of it may be wrong at the foundational level. There is a single number in cosmology known as the Hubble constant. It quantifies the rate at which the universe is expanding. It is arguably the most important number in the entire discipline, because once you know it, a whole series of other quantities fall into your lap. The age of the universe, the size of the observable universe, the long-term future of the cosmos itself. Nail this one number, and the rest of cosmology starts arranging itself into a coherent picture. Get it wrong, and everything downstream disintegrates. For decades now, scientists have approached the Hubble constant from 2 independent directions. The first approach examines the cosmic microwave background, the faint radiation left over from when the universe was only 380,000 years old. Using information gathered by the European Space Agency's Planck satellite, cosmologists turned that ancient glow into a map, fed it into the standard model of cosmology known as lambda CDM, and calculated an expansion rate of approximately 67.5 kilometers per second per megaparsec. The second approach takes an entirely different road. Known as the cosmic distance ladder, it relies on astronomers first measuring the distances to nearby stars, then using those distances to calibrate the distances to more remote galaxies, and from all of that, calculating how fast the universe seems to be expanding in our own cosmic backyard. That method has consistently been returning values in the range of 73 to 76 kilometers per second per megaparsec. A difference of 6 or 7 units may sound trivial. In precision cosmology, it is seismic. And by late 2025, the disagreement had climbed to what physicists call 5 sigma. 5 sigma is the gold standard for declaring a discovery in physics. It is precisely the threshold that was crossed when researchers at CERN confirmed the existence of the Higgs boson. This is no longer a friendly scientific quibble. Daniel Skolnick, a physicist at Duke University, said it without filters. He said that we have been dancing around this Hubble tension for years, And at a certain point, the community has to stop pretending it is not a serious wound. Throughout 2024 and 2025, the James Webb Space Telescope was pointed back at the same Cepheid variable stars that had anchored the local measurements. The goal was simple enough: rule out the possibility that dust grains along the line of sight or systematic errors inside the instruments had been quietly skewing the distance measurements. The outcome was unambiguous. The original numbers held up beautifully. The local value of roughly 73 kilometers per second per megaparsec is airtight. Then, in December of 2025, the TDCOSMO collaboration published an entirely separate measurement using gravitational lensing, a technique that tracks how light from distant quasars bends as it travels past foreground galaxies. Their answer agreed with the local measurement, not with the Planck one. Every new independent method that takes a reading of the expansion rate close to us delivers the same figure. And that figure is the one that the standard model says should not be possible. Lambda CDM, which has endured every serious stress test thrown at it for a full quarter of a century, may now be genuinely splitting open. And the fractures do not end at the expansion rate. In January 2026, NASA announced the confirmation of the most distant galaxy ever caught in a telescope. It carries the catalog name MOM-Z14, and it sits at a redshift of 14.44. That means the photons leaving its stars have been riding a tide of expanding space toward us for more than 13.5 billion years. We are seeing this galaxy as it existed when the universe was only 280 million years old, when it had barely completed 2% of its current lifespan, and it has no business appearing the way it does. MOM-Z14 is brighter, more compact, and more chemically developed than any theoretical prediction for a galaxy of its age. It contains elevated levels of nitrogen, an element that ordinarily requires several successive generations of stars to manufacture. But 280 million years simply does not allow enough time for those generations to cycle. The galaxy has even scrubbed its local surroundings free of primordial hydrogen, something astronomers had assumed no object could accomplish at such an early epoch. Rohan Naidu of the Massachusetts Institute of Technology, who led the study, said the punchline plainly. He said that with Webb we are peering deeper into the past than any generation of humans before us, and the view we are being handed looks nothing like the picture our theories painted. And MOM-Z14 is not a lone outlier. The James Webb Space Telescope has now identified over 100 bright galaxies at redshifts above 10, in an era when the best pre-launch forecasts expected essentially none. The population of bright galaxies at that cosmic distance is more than 100 times denser than any consensus model predicted. Tucked into the same population is Zhulong, a Milky Way-sized spiral galaxy pinned down at a redshift of 5.2, only about 1 billion years after the Big Bang, already displaying a fully developed central bulge, fully formed spiral arms, and a stellar mass of around 100 billion suns. It looks like a galaxy that has had billions of years to smooth itself into the shape we see. It had a few hundred million. Jacob Shen, a postdoctoral researcher at MIT and a member of the MOM-Z14 research team, summarized the mood of the field in a single sentence. He said there is a widening chasm between theory and observation in our view of the early universe. The Big Bang itself remains untouched. The cosmic microwave background, the abundances of the lightest elements, the continuing expansion of space, all of them still point to a hot, dense origin roughly 13.8 billion years ago. What is buckling is the timeline afterward. Galaxies are forming too quickly, shining too brightly, and organizing themselves too thoroughly for the Lambda CDM model to accommodate. Something crucial is missing from our picture. And if our model of the universe is failing, what else might we have gotten wrong? How much of actual reality have we never once laid eyes on? To begin to answer that, we have to start with what we do know. We have to start close to home and travel outward step by step. And the first lesson we meet close to home is a humbling one, because even the distances within our own tiny solar system are enough to make it painfully clear that this universe was not designed with our convenience in mind. Chapter 2. You are here, and you are nothing. Let us open with the nearest thing we have, the moon. It hangs up there in the sky, seeming close enough that you could reach up and brush it with your fingertips. Poets have written about it for centuries as a companion, a familiar face, a traveler keeping pace with us through the dark. The moon is not close. It is 400 kilometers away. That is enough room to line up 30 Earths in a tidy row between us and our own satellite. A rocket that reaches escape velocity needs about 3 days to complete the crossing. A Formula One car running flat out at top speed would require 42 days. And this is the nearest celestial body to us. This is the very first stair on the staircase. And already it takes 3 days of sustained travel at roughly 28,000 kilometers per hour. Now take the next step. Mars. The red world that fills our imagination every time someone starts talking about turning us into a species that lives on more than one planet. Mars, at its closest approach, sits around 55 million kilometers away from us. At its farthest, it stretches to over 400 million kilometers. On average, the distance is roughly 225 million kilometers. That is 585 times farther than the moon. A radio signal sent at the speed of light, the fastest possible transmission any physics allows, takes anywhere between 3 and 21 minutes to make the one-way crossing between our two worlds. When NASA sends a new command to the Curiosity rover, the control team has to sit on their hands for up to 21 minutes just to find out whether the message was received. A normal conversation is unthinkable. Real-time interaction is impossible. Mars is right next door, and it is already beyond the reach of a phone call. In 2014, Curiosity turned its cameras upward and took a photograph of Earth from the surface of Mars. In that image, our entire home planet is a faint bluish pinprick hanging in the Martian sky. Not a jewel, not a marble, a dot, barely distinguishable from the background stars. Everything you have ever known, every person you have ever held, every city you have ever walked through, every war ever fought, every song ever sung, condensed into a single smudge of light in another world's sky. And that is from Mars, our nearest planetary neighbor. Now let us try to leave the solar system. Or rather, let us try, because it turns out that escaping this solar system is almost unreasonably difficult. The farthest manufactured object in existence is Voyager 1. It launched in 1977. It has been traveling without pause for over 47 years at a velocity of roughly 61,200 kilometers per hour. As of right now, it is approximately 24.6 billion kilometers from Earth. That is impressive. Nothing humans have ever built has reached further. But Voyager 1 has not left the solar system. It is not even close to leaving. The solar system is considerably larger than most people imagine. Beyond the planets, beyond the Kuiper belt where Pluto orbits in its long, lazy cycle, there is an enormous spherical shell of icy debris called the Oort cloud. It extends from around 2,000 astronomical units to perhaps 100,000 astronomical units out from the Sun. 1 astronomical unit is simply the distance from Earth to the Sun, roughly 150 million kilometers. Voyager 1 currently sits at around 165 astronomical units. It will not reach even the inner edge of the Oort cloud for another 300 years, and it will not emerge out the other side for approximately 30,000 years. 30,000 years. That is longer than the whole of recorded human history. Longer than the entire span from the first cave paintings on the walls of Lascaux to the exact moment in which you are listening to this voice. And at the end of those 30,000 years of travel, Voyager will have done nothing more than exit the immediate neighborhood of our own sun. It will not have arrived anywhere near another star. The nearest star to our sun is Proxima Centauri, 4.24 light-years away. At Voyager's present speed, the probe would need more than 73,000 years to reach that neighbor. If Voyager 1 had been launched at the very dawn of modern human civilization, when the first cities were being raised out of the mud of Mesopotamia, it would still not have arrived there yet. Bolted to the side of Voyager 1 is a gold-plated phonograph record, known as the Voyager Golden Record. It holds 48 images encoded as audio signals, greetings in 55 languages, 27 musical compositions spanning Bach, Chuck Berry, and Japanese gamelan, sounds of our planet such as thunder, wind, bird song, and the soft sound of a mother kissing her child. It was assembled by a committee chaired by Carl Sagan. The record is a message in a bottle flung into a cosmic ocean. It was intended to say who we are, what we sound like, and what we consider beautiful, to anyone who might stumble across it. The odds that anyone ever will are essentially zero. Space is too big. The distances are too vast. Voyager 1 will drift through interstellar space for millions and possibly billions of years. The record will outlast every skyscraper, every nation, every language ever spoken on Earth. It will outlast the sun itself. And in all probability, no set of hands will ever reach down, pick it up, and place the stylus in the groove. It is the loneliest artifact we have ever made. A love letter with no intended recipient, adrift in darkness. Perhaps the most humbling measure of our insignificance is not how far Voyager has gone, but how far our voice has carried. Since the early 20th century, humanity has been leaking radio and television signals into space. These electromagnetic waves travel at the speed of light. They are the fastest product we have ever manufactured. And they have been spreading outward from Earth for around 125 years, forming an expanding sphere of human noise 125 light-years in radius. That sounds like a reasonable distance. It is not. The Milky Way spans 100,000 light-years from side to side. It contains an estimated 250 billion stars. Our radio bubble, 125 light-years in radius, encompasses a few thousand of those stars at most. If you dropped our radiosphere into a map of the Milky Way, it would vanish. An invisible mote. A single grain of sand on a beach that wraps around the horizon. Beyond 125 light-years from Earth, no civilization anywhere has had the opportunity to hear us. No signal has reached them. No evidence of our existence has arrived. For all cosmic purposes, we are silent. We have been shouting into the darkness for a century, and the darkness has not noticed. And here is the thought that should keep you up tonight. The Milky Way, this immense spiral beacon that dwarfs everything we have ever known, is itself only one galaxy. One galaxy among 2 trillion in the observable universe. And as recently as 1920, we did not even realize that other galaxies existed. In 1920, the astronomical community convened what came to be known as the Great Debate. On one side stood Harlow Shapley, who argued that the Milky Way was the entire universe, and that those fuzzy patches of light seen through telescopes, the so-called spiral nebulae, were simply gas clouds somewhere inside our galaxy. On the other side stood Heber Curtis, who argued that at least some of those nebulae were actually distant galaxies, island universes far outside the boundaries of the Milky Way. The debate was finally settled in 1924 when Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, identified Cepheid variable stars inside the Andromeda Nebula. These stars pulse at rates that are directly linked to their intrinsic brightness, which allows astronomers to compute their distance. Hubble measured the distance to Andromeda and found it to be approximately 900,000 light-years away, far too remote to sit inside the Milky Way. Andromeda was a separate galaxy. Later, more accurate measurements pushed the distance to about 2.5 million light-years. In a single observation, the universe ballooned to a scale no one had previously imagined. What had been considered the totality of reality, the Milky Way, was suddenly revealed to be one island in a vast archipelago of galaxies stretching out to the edge of what telescopes could see. And that archipelago, we would later discover, is neither uniform nor still. It has architecture. It has patterns. It has enormous zones of terrifying emptiness. Emptiness so absolute that if you lived at their center, you would be unaware that the rest of the universe even existed. The universe is not merely large, it is largely nothing, and the somethings inside it have organized themselves into a structure so sprawling and so unfamiliar that only now, well into the first decades of the 21st century, are we beginning to perceive it clearly. That pattern starts with the voids, the enormous dark rooms between the galaxies, the vast regions where the lights switch off and almost nothing remains. Chapter 3. The Great Nothing. In 1981, an astronomer named Robert Kirshner at the University of Michigan was running what at the time was considered a fairly routine redshift survey. His team was mapping the positions of galaxies in 3 dimensions, measuring not only their apparent positions on the sky, but also their actual distances from Earth. Galaxy surveys had been done before. This one was supposed to be business as usual. But when Kirshner's team plotted their data across a patch of sky in the direction of the constellation Bootes, something stared back at them that was not supposed to be there. A gap. An enormous, roughly spherical gap in the distribution of galaxies. They double-checked their instruments. They re-examined their data. The gap was genuine. They had discovered the Bootes void. The Bootes void is a very nearly spherical region of space, approximately 330 million light-years across. To appreciate that figure, consider that the entire Milky Way is 100,000 light-years wide. You could line up more than 3,000 Milky Way-sized galaxies across the diameter of the Bootes void. It is one of the largest voids ever identified in the observable universe, and it is almost completely empty. In a volume of space that size, astronomers would ordinarily expect to find roughly 2,000 galaxies. The Bootes void contains about 60 galaxies inside a volume that should comfortably hold thousands. And those 60 galaxies are not even scattered uniformly. They are threaded along a thin tubular structure that cuts through the middle of the void, like a few crumbs caught along a string running through an otherwise empty room. The rest of it is darkness. Nothing. An ocean of vacuum with no land in sight. The astronomer Greg Aldring once described the loneliness of the Bootes void with a thought experiment that captures the feel of the place better than any statistic can manage. He said that if the Milky Way had been placed at the very center of the Bootes void, we would not have realized that other galaxies existed until the 1960s. Sit with that for a moment. We would have aimed every telescope of the 19th and early 20th centuries at the sky, and we would have seen nothing. No Andromeda, no Magellanic Clouds, no spiral nebulae to argue about. We would have believed, with every available piece of evidence in our hands, that we were alone in an infinite dark ocean, and we would have been wrong. But there would have been no way for us to know it. The Bootes void is not an exception. It is one specimen of a feature that dominates the architecture of the universe: voids. Enormous, roughly spherical regions of below-average galaxy density that collectively account for approximately 80% of the observable universe by volume. 80%. The overwhelming majority of the universe is not full of stars and planets. It is full of almost nothing. The places where matter actually collects, the galaxies, the clusters, the superclusters, form the minority. They cling to thin walls and slender filaments between the voids, like soap film stretched around a bubble. On its largest scale, the universe looks like foam. Enormous chambers of emptiness separated by impossibly thin membranes of lit matter. And here is the truly unsettling addition: you live inside a void. The Milky Way is embedded in what astronomers call the KBC void, also known as the local hole. It is named after Ryan Keenan, Amy Barger, and Lennox Cowie, the researchers who first mapped it in 2013. The KBC void is a region of below-average galaxy density, about 2 billion light-years across. 2 billion light-years. That is more than 6 times the width of the Bootes void. We are not sitting in a normal portion of the universe. We are not parked in a bustling metropolitan region of the cosmic web. We are in a relatively empty zone, an under-dense hollow, where there are somewhere between 15% and 50% fewer galaxies than in the surrounding cosmic neighborhoods. The Milky Way orbits within a few hundred million light-years of the center of this void. In a very real sense, we are residents of the cosmic suburbs, the stretch of sky where the street lamps thin out and the houses are set far back from the road. And this is not merely a curiosity for mapmakers. The KBC void may have genuine consequences for the way we interpret the universe. Some researchers have proposed that living inside a large underdense region could itself be contributing to the Hubble tension, the crisis we opened with at the top of this journey. The reasoning runs like this. Galaxies inside a void experience a subtle gravitational pull from the denser regions surrounding the void. That pull accelerates the local expansion of space, making it appear as though our neighborhood is stretching faster than the cosmic average. If the KBC void is real, and if we sit near its center, our local measurements of the expansion rate would naturally come back higher than the value derived from the cosmic microwave background. The disagreement between the two numbers would not be a symptom of broken physics. It would be a consequence of an unusual address. Data presented at the National Astronomy Meeting in 2025 using baryon acoustic oscillation measurements suggested that a void-based model is approximately 100 million times more likely than a void-free model consistent with the Planck cosmology value. Other researchers disagree. The question remains open, but the implication is striking on its face. The deepest crisis in modern cosmology may be caused in part by the simple fact that we inhabit a relatively quiet corner of the universe. Our perception of reality may be distorted by our location. But where did the voids come from in the first place? Why is the universe organized this way? Why is 80% of the cosmos effectively a desert? The answer reaches all the way back to the very beginning, to the first fractions of a second after the Big Bang. When the universe was born, it was not perfectly uniform. It was almost uniform, almost perfectly smooth, hot, and dense, but not entirely. Quantum mechanics, the physics governing the behavior of the subatomic, guarantees that tiny random fluctuations existed in the density of matter and energy from the very first instant. These fluctuations were unimaginably small, variations of roughly 1 part in 100,000. If the early universe had been a perfectly still ocean, these fluctuations would have been ripples smaller than a millimeter on a surface spanning thousands of kilometers. But gravity is patient, and gravity does not forget. Over billions of years, gravity amplified those minor differences. Regions that happened to be slightly denser than average pulled extra matter toward themselves. Regions that happened to be slightly less dense leaked matter to their denser neighbors. It was a cosmic feedback loop. The rich got richer, the poor got poorer. Dense pockets grew denser, empty stretches grew emptier. Over cosmic time, the faint variations in density swelled into the vast structures we see today. Matter condensed into thin sheets and delicate filaments. The spaces between them expanded and drained, becoming the voids. The universe, shaped by the very same quantum jitter that governs the behavior of subatomic particles, organized itself into a web. An enormous interconnected network of matter and emptiness, stretching across the entire observable cosmos. The cosmic web is defined more by what is absent than by what is present. The voids are not holes punched through an otherwise solid universe. They are the default state. Emptiness is the rule. Matter is the exception. The galaxies, the stars, the planets, the atoms that compose your body, all of it exists on thin, glowing threads, strung between enormous rooms filled with nothing. If 80% of the universe is void, what fills the remaining 20%? The answer is a structure so vast and so intricate that it took decades to fully grasp. A lattice so enormous that it extends across the entire observable universe. And in 2025, for the very first time in human history, we photographed a single piece of it, a single strand of the biggest object in existence. A highway of gas and dark matter stretching 3 million light-years between two ancient galactic hosts. A single thread of something called the cosmic web. And what that photograph revealed is that the universe is not a random scattering of galaxies. It is a machine, a living, circulating, spinning machine built on an invisible scaffold we are only now beginning to perceive. Chapter 4. The Web. The universe is not a disorganized dust of galaxies floating through space the way motes drift in a sunlit room. It has a skeleton. It has architecture. A vast interconnected network of filaments and nodes and voids that stretches across the entirety of the observable universe and beyond. Scientists call it the cosmic web, and it is the single largest structure in existence. The term cosmic web was coined in 1996 by the cosmologist Richard Bond. But the idea behind it had been building for years before that. As galaxy surveys grew more detailed through the 1980s and 1990s, astronomers began to notice that galaxies were not distributed evenly across the sky. They clumped. They lined up into chains. They gathered along invisible corridors. Between those corridors lay the enormous empty voids. The pattern was unmistakable. At the very largest scales, the universe had organized itself into something that looked like a three-dimensional spider's web. Bright filaments of galaxies connecting massive nodes called galaxy clusters, with dark, empty voids filling the space in between. The filaments are enormous. Individual strands can run for hundreds of millions of light-years. They're built from dark matter, gas, and galaxies. all dragged together by gravity into elongated structures that serve as highways connecting the densest regions of the cosmos. Where filaments meet, galaxy clusters form. These are the nodes of the web, the largest gravitationally bound structures in the universe. A single node may contain hundreds or thousands of galaxies, vast pools of superheated gas, and enormous halos of dark matter. Our own local group, a modest collection of roughly 100 galaxies that includes both the Milky Way and the Andromeda Galaxy, lives on a filament. That filament connects the Fornax cluster to the Virgo cluster. We do not sit at a node, we do not occupy an intersection. We live on a back road between two galactic metropolises. For decades, the cosmic web existed primarily in computer simulations and in the pages of mathematical models. Supercomputers could simulate the evolution of the universe from the Big Bang to the present day and would consistently produce web-like structures that matched the observed distribution of galaxies. The theory was robust. The models were elegant. But directly imaging a filament, capturing the faint glow of the gas and matter inside one, remained beyond our reach. The gas in the filaments is extraordinarily diffuse. Hydrogen, the most abundant element in the universe, emits only the faintest of luminosities when it is spread across millions of light years. Detecting that glow is a little like trying to photograph the flicker of a candle from the far side of a continent. Then in 2025, an international team led by Davide Tornatore, a doctoral student at the University of Milano Bicocca, working with the Max Planck Institute for Astrophysics, finally accomplished what astronomers had been hoping for across multiple decades. They captured the first high-definition direct image of a cosmic web filament. The filament they imaged runs 3 million light-years between two galaxies, each of which hosts an active supermassive black hole at its center. The two galaxies sit at a redshift of 3, which means the light from the filament has been traveling toward our telescopes for nearly 12 billion years. When the filament was glowing the way their image shows it, the universe was only around 2 billion years old. We are looking at the cosmic web in its adolescence. The team used the multi-unit spectroscopic explorer, known as MUSE, mounted on the European Southern Observatory's Very Large Telescope in Chile. MUSE is an extraordinary instrument. It collects full spectra for every pixel in its field of view, which allows astronomers to peel the faint hydrogen emission of a filament cleanly away from the background noise. Even with MUSE, the task demanded more than 150 hours of observation of the same single patch of sky. 150 hours of a world-class telescope staring at one fixed point in the universe, collecting one photon at a time, slowly building up an image from the dimmest light imaginable. The result was published in Nature Astronomy, and it was stunning. The image showed the diffuse gas inside the filament stretching between the two galaxies like a luminous bridge. The researchers could even trace the boundary between the gas that belonged to the galaxies themselves and the material flowing along the cosmic web. For the first time in history, the connection between a galaxy and the web that feeds it had been directly observed. When they held their image next to the supercomputer simulations from the Max Planck Institute, the agreement was striking. The shape, the density profile, the brightness pattern of the observed filament all matched the theoretical predictions almost exactly. The simulations had been correct all along. The cosmic web is real. It looks exactly the way the models said it would look. And now we finally have a photograph to prove it. But the cosmic web is not a static scaffold. It is not a frozen frame holding galaxies in place. It is alive, dynamic, in motion. In late 2025, researchers at the University of Oxford published a remarkable discovery in the monthly notices of the Royal Astronomical Society. Using data from the Meerkat radio telescope in South Africa, they found one of the largest rotating structures ever recorded, a chain of 14 galaxies embedded in a cosmic filament 5.5 million light-years long. All 14 galaxies are spinning in the same direction. The entire filament, a structure several million light-years across, is rotating as a unit. This caught the field by surprise. The conventional picture of filaments had them cast as passive structures, pieces of gravitational scaffolding that matter tumbles onto and flows along. But the Oxford discovery revealed that filaments are actively transporting angular momentum, the energy of rotation, across enormous distances. They are not merely highways. They are rivers. Rivers of gas, of matter, and of rotational energy, all of it pouring into the galaxies at the nodes, feeding them, setting them spinning, sculpting their shapes. The cosmic web is the circulatory system of the universe. It is the network through which matter and energy flow from the voids into the crowded intersections where galaxies are born, nurtured, and grown. Without the web, galaxies would have no supply line, no incoming raw material. They would eventually burn through their gas reserves and slowly flicker out. The web keeps them alive. And the web itself is constructed from something we cannot see, something that accounts for 85% of all matter in the universe. Something that does not emit light, does not absorb light, does not reflect light. Something we know exists only by virtue of its gravitational effect on everything else around it. The dark matter that forms the invisible skeleton of the cosmic web is the single most abundant form of matter in the universe, and we have never directly detected a single particle of it. Every filament, every node, every galaxy cluster in the web sits cradled inside a halo of dark matter. The dark matter came first. It collapsed under its own gravity long before ordinary matter could, forming the scaffolding onto which gas and, eventually, stars would accumulate. The galaxies we see are simply the luminous frosting on an invisible cake. The real structure, the real architecture of the universe is dark. In 2024, researchers at Yonsei University achieved a milestone using data from the Subaru telescope. They made the first detection of dark matter sitting directly on cosmic web filaments in the Coma cluster region. They employed gravitational lensing, the bending of light from more distant background galaxies as that light passes through the mass of the filament, to map the dark matter distribution along the strands of the web. The dark matter was there, right where the models had always said it would be, invisible but heavy, shaping everything around it. The cosmic web is the actual structure of the universe. Not the galaxies, not the stars, not the planets. Those are ornamentation. The web is the frame. And the frame is built out of darkness. It is held together by a substance we cannot see, and driven by a force we cannot explain. And when you zoom out far enough to take in the web in its entirety, you realize something that rearranges the way you think about your place in reality. You are not living in a universe scattered with galaxies. You are living on a thread of the web. A single glowing strand in a lattice of threads, surrounded on every side by the vast, cold, silent emptiness of the voids, clinging to a filament like a droplet of dew on a spider's web. And the spider, if any spider exists, is invisible. Chapter 5. The Dark Scaffold. Here is a number that should leave you uncomfortable. 5%. That is how much of the universe you are able to see. That is how much of the universe is made of the kind of matter you learned about in chemistry class. Protons, neutrons, electrons, atoms, molecules, stars, planets, gas clouds. Everything you have ever touched, tasted, measured, or detected with any instrument anyone has ever built. All of it. 5%. The remaining 95% is composed of two substances. 27% is dark matter. 68% is dark energy. Between the two of them, they own the cosmos completely, and we do not understand either one. Let us begin with dark matter. It was first proposed in the 1930s by the Swiss astronomer Fritz Zwicky. He was studying the Coma cluster, a massive collection of galaxies roughly 320 million light-years from Earth. He measured the speeds at which the galaxies within the cluster were moving, and he found something very odd. They were moving too fast. Far too fast for the visible matter in the cluster to hold them together through gravity alone. The galaxies should have flown apart long ago. Something invisible was supplying the extra gravitational glue. Zwicky called it Dunkelmaterie, dark matter. For decades, the idea was largely shrugged off. It seemed too strange, too speculative. Then, in the 1970s, the American astronomer Vera Rubin made the same discovery on a smaller scale. She was measuring the rotational speeds of stars inside spiral galaxies. According to Newtonian gravity, stars on the outskirts of a galaxy should orbit more slowly than stars close to the center, in the same way that the outer planets of our solar system orbit the Sun more slowly than the inner ones. But Rubin found that the rotation curves were flat. Stars near the edges of galaxies were moving just as quickly as stars near the core. The only explanation that worked was that a massive halo of invisible matter extended far beyond the visible disk of every galaxy, providing the gravitational tug needed to keep the outer stars in their orbits. Since then, the evidence for dark matter has piled up from every conceivable direction. Galaxy clusters bend the light of objects behind them more strongly than their visible mass can account for, a phenomenon known as gravitational lensing. The cosmic microwave background contains patterns that only make sense if dark matter was present in the early universe, carving out gravitational wells into which ordinary matter later fell. And the cosmic web itself would not have formed without dark matter. Simulations that include only ordinary matter produce a universe that looks nothing like the one we live in. Add dark matter, and the web emerges. The filaments form. The voids open. The galaxies cluster at the nodes. Dark matter is not a minor ingredient. It is the main ingredient. It makes up 85% of all matter in the universe. And yet we have no idea what it is. Dozens of experiments around the world are hunting for dark matter particles. Underground detectors in old mines, shielded from cosmic rays by kilometers of rock. Particle accelerators like the Large Hadron Collider at CERN, smashing protons together at nearly the speed of light, hoping that dark matter particles will appear in the debris. Space telescopes, scanning for the gamma-ray signatures of dark matter particles annihilating each other. None of these experiments has produced a confirmed detection. The most popular candidate, a class of hypothetical particles called weakly interacting massive particles, has stubbornly refused to reveal itself. After decades of searching, we know dark matter is there. We can map out its distribution. We can measure its effects with exquisite precision. But we have never once held one of its particles in a detector. Now let us turn to the even stranger member of the dark family, dark energy. In 1998, two teams of astronomers made a discovery that would earn them the Nobel Prize in Physics in 2011 and rattle cosmology to its foundations. They were studying a specific variety of exploding star known as a type Ia supernova. These supernovae are extraordinarily useful because they all reach roughly the same peak brightness when they detonate, which makes them excellent distance markers. By measuring how bright a type Ia supernova looks from Earth and comparing that observed brightness to its known true brightness, astronomers can work out exactly how far away it is. The two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using these supernovae to reconstruct the expansion history of the universe. The expectation was straightforward. The expansion should be slowing down. Gravity, the attractive force between all matter, should have been gradually pulling everything back together, decelerating the expansion that had started at the Big Bang. The result told a different story. The distant supernovae were dimmer than expected. They were farther away than they should have been. The expansion of the universe was not slowing down. It was speeding up. Something was pushing space apart. Something was overpowering the collective gravitational attraction of every particle of matter in the universe and forcing the expansion to accelerate. Something with no known source, no identified mechanism, and no precedent anywhere in physics. Scientists named it dark energy, a name that frankly admitted their ignorance. It is dark because we cannot see it. It is energy because it does something, and that something is driving the universe apart. Dark energy is not a force in the ordinary sense. It does not push galaxies apart the way a rocket engine pushes a capsule off of Earth. Instead, it appears to be a property of space itself. It causes space to stretch, and the more space there is, the stronger its effect becomes. As the universe grows, more space is created, which generates more dark energy, which drives further expansion, which creates still more space. It is an accelerating cycle, and it is winning. The consequences are profound. Distant galaxies are receding from us faster and faster. Galaxies beyond a certain distance are already receding from us faster than the speed of light. Not because they are moving through space faster than light, which is physically impossible, but because the space between us and them is expanding faster than light can cross it. Any light those galaxies emit right now will never reach us. They are lost to our view forever, carried beyond the horizon by the expansion of the universe itself. Dark energy accounts for 68% of the total energy content of the universe. Dark matter accounts for 27%. Ordinary matter, everything you can see and touch, everything that makes up every star and every planet and every atom in your body, comes in at 5%. 5%. We understand 5% of what the universe is made of. The greatest structure ever discovered, the cosmic web, is built on a scaffold of dark matter we have never directly detected, driven by dark energy we cannot explain. And everything visible in the night sky is a thin, luminous film, stretched across an abyss of invisible forces. Every telescope, every experiment, every spacecraft we have ever built has been studying the 5%. The decoration, the frosting, the visible crust on an invisible machine of staggering complexity. And if we barely understand what the universe is made of, how can we trust our map of how big it is? How can we be confident in our models when 95% of reality remains unexplained? The answer is that our confidence is wavering. Our models are buckling under the weight of new observations. And the map, as we are about to see, is starting to contradict itself. Because somewhere out there, hidden behind the dust and gas of our own galaxy, something enormous is pulling us. The Milky Way and 400 other galaxies are hurtling through space at over 2 million kilometers per hour toward a region of space we cannot fully see. A gravitational anomaly so powerful that it dominates the motion of everything within hundreds of millions of light years. And we still do not know for certain exactly what it is. Chapter 6. The Invisible Hand. The Milky Way is not sitting still. Nothing in the universe is sitting still. Everything is moving. Planets orbit stars. Stars orbit the centers of their galaxies. Galaxies orbit each other inside clusters. Clusters flow along the filaments of the cosmic web. But layered on top of every one of these motions, there is something else. A pull. A vast, steady gravitational pull dragging the Milky Way and roughly 400 other galaxies in a specific direction at an astonishing speed, 600 kilometers per second. That is 2.2 million kilometers per hour. Every second that passes, the Milky Way moves 600 kilometers closer to a region of space in the direction of the constellation Centaurus, roughly 150 to 250 million light-years away. We are not drifting, we are racing, and the destination is something we can only barely see. Scientists call it the Great Attractor. The Great Attractor was first identified in the 1980s by a team of 7 astronomers, later nicknamed the Seven Samurai, led by Alan Dressler. They had been mapping the peculiar velocities of galaxies, the velocities that deviate from the smooth cosmic expansion. When they plotted those motions, they found that an enormous swath of the cosmos was streaming in the same direction. Hundreds of galaxies all converging on a single gravitational center. Something was pulling them. Something massive. Something that did not show up in the optical surveys. The problem was its location. The Great Attractor lies behind what astronomers call the zone of avoidance. This is the region of the sky that is blocked from our view by the disk of the Milky Way itself. Our own galaxy, the very platform from which we observe the rest of the universe, sits directly in the way. The dust, gas, and dense starfields lying in the plane of the Milky Way absorb and scatter the light coming from anything behind them. It is a little like trying to make out a distant mountain through a wall of fog. You know something is there because you can feel its gravitational influence, but you cannot get a clean picture of it. Over the decades, astronomers have used wavelengths other than optical light to peer through the zone of avoidance. X-ray surveys in the 1990s revealed the Norma cluster, also cataloged as Able 3627, sitting almost exactly at the estimated position of the Great Attractor. Norma is a massive galaxy cluster, but when they added up its total mass, it fell short. Only about 1/10 of the gravitational pull needed to explain the observed motions of all those galaxies could be attributed to Norma alone. Norma could not be the Great Attractor on its own. Something even larger had to be hiding behind it, and something is. Farther along the same line, even more remote and even more massive, sits the Shapley supercluster, sometimes called the Shapley concentration. It is one of the most massive structures in the observable universe, a dense collection of galaxy clusters and superclusters, roughly 650 million light-years from Earth. Some researchers now suspect that the Great Attractor is not really a destination at all. It is more like a waypoint. a gravitational rest stop on the highway to the Shapley supercluster. The true source of the pull may be distributed across that much larger, much more distant structure. In 2014, a breakthrough reorganized the whole picture. A team led by Brent Tully of the University of Hawaii published a paper in Nature that redrew the cosmic map. Using galaxy flow data, they mapped out the gravitational basin in which the Milky Way and thousands of other galaxies reside. They named this basin Laniakea. Laniakea is Hawaiian for immeasurable heaven. It spans 520 million light-years across and contains approximately 100,000 galaxies. The Great Attractor sits at its gravitational heart. Every galaxy inside Laniakea is flowing toward that central region, pulled by the combined gravitational influence of the dark matter and visible matter concentrated there. We are inside Laniakea. We are one of its 100,000 galaxies. We are falling toward its center. But here is the paradox. We will never get there, because the universe is expanding, and that expansion is accelerating. Dark energy, the mysterious force that fills 68% of the cosmos, is stretching the space between galaxy clusters faster than gravity can pull them together. The Great Attractor is pulling us, but the expansion of space is pulling us apart. We are approaching the attractor at 600 kilometers per second, yet the space between us and it is stretching at a rate that will eventually exceed our approach speed. The Milky Way is on a journey it will never complete. We are falling toward a destination we will never reach. Gravity gives us direction. Dark energy denies us arrival. It is motion without purpose. An infinite approach toward an unreachable center. And this is the fundamental character of the universe on its largest scales. Everything is in motion. Everything is interconnected by gravity. But the expansion wins in the end. Over billions of years, the universe will continue to stretch apart. Galaxy clusters that are not gravitationally bound to each other will eventually drift beyond each other's cosmic event horizons. They will become invisible to each other, unreachable, simply lost. And yet for now, in this brief cosmic moment, the architecture holds. The web is intact. The filaments are flowing, the nodes are growing, the Great Attractor pulls, and the galaxies respond. We are part of a structure, a vast, interconnected gravitational organism that spans hundreds of millions of light-years. We now have the pieces, the voids, the filaments, the dark scaffold, the invisible hand. It is time to assemble the full picture. To zoom out as far as the eye can be forced to see. To write out our full cosmic address from Earth to the edge of the observable universe. And each layer of that address will dwarf the one before it in a way that is almost impossible to process. Because the universe is not just big, it is structured to be big. It is organized, layered, nested. Each container impossibly larger than the last. Your cosmic address begins here on a small rocky planet circling an ordinary star, and it ends at the edge of everything we can see. A boundary so distant that the light coming from the other side has been traveling for 13.8 billion years and has still not arrived. But even that boundary is not the end. It is not even close. The observable universe, all 93 billion light-years of it, may itself be nothing more than a keyhole. And the room on the other side of the keyhole may be unimaginably, terrifyingly larger than anything we have so far calculated. Let us construct the address step by step, layer by layer, and see just how small we truly are. Chapter 7. Your Cosmic Address. Let us build it from the ground up. Your cosmic address. Every layer larger than the last. Every step a revelation in scale. You are on Earth. A rocky planet 742 kilometers in diameter. It orbits a star we call the Sun, a middle-aged yellow dwarf roughly 4.6 billion years old. The Sun is one star among 250 billion in the Milky Way galaxy. It is not special. It is not central. It is a perfectly ordinary star in a perfectly ordinary part of the galaxy. The Sun and its planets make up the solar system. The solar system sits within a small region of diffuse interstellar gas called the local interstellar cloud. This cloud is about 30 light-years across, and the Sun has been passing through it for roughly 44,000 years. The local interstellar cloud itself sits inside a much larger structure called the local bubble. The local bubble is a region of hot, low-density gas approximately 1,000 light-years across. It was carved out by a series of supernova explosions over the past 10 to 20 million years. Those explosions scoured away the denser interstellar medium and inflated a cavity of thin, hot plasma. We are inside that cavity. The local bubble, in turn, sits within one of the Milky Way's spiral arms, specifically the Orion arm, sometimes called the Orion spur. It is a minor arm, a bridge between two larger spiral arms, the Sagittarius arm and the Perseus arm. The Orion arm is roughly 500 light-years wide and 10,000 light-years long, and the Orion arm is one feature of the Milky Way galaxy itself. Our galaxy is a barred spiral, roughly 100,000 light-years in diameter and about 1,000 light-years thick at the disk. It contains an estimated 250 billion stars and probably more planets than stars. At its center sits a supermassive black hole known as Sagittarius A*, with a mass of roughly 4 million times that of the Sun. Until 1920, most astronomers believed the Milky Way was the entirety of the universe. The great debate of that year between Harlow Shapley and Heber Curtis turned on the question of whether those fuzzy patches called spiral nebulae were structures within our galaxy or separate galaxies entirely. When Edwin Hubble used Cepheid variable stars to prove that the Andromeda Nebula was a separate galaxy millions of light-years away, the universe expanded overnight. Not physically, conceptually. Humanity understood for the first time that our galaxy was one island in an archipelago of galaxies stretching out as far as any telescope could see. Now let us zoom further. The Milky Way is not alone. It is one of roughly 100 galaxies in a gravitationally bound collection called the local group. The local group spans approximately 10 million light-years. Its two largest members are the Milky Way and the Andromeda galaxy. Andromeda is roughly 2.5 million light-years away and contains about 1 trillion stars. Andromeda and the Milky Way are on a collision course. In about 4.5 billion years, the two galaxies will merge in a slow gravitational dance that will reshape both of them into something new. The local group also contains the Triangulum galaxy, about 60 smaller galaxies, and numerous dwarf galaxies. Together, these galaxies orbit their common center of gravity, bound together by the gravitational influence of their combined mass, the majority of which is dark matter. The local group is part of a much larger structure called the Virgo supercluster. The Virgo supercluster contains roughly 100 galaxy groups and clusters spread across 110 million light-years. At its heart is the Virgo cluster itself, a massive collection of over 300 galaxies roughly 54 million light-years from Earth. The Virgo cluster dominates the supercluster gravitationally. We are on its outskirts, a minor local group orbiting at the edge of a much larger gravitational kingdom. But even the Virgo supercluster is just a lobe of something grander. In 2014, Brent Tully and his team revealed Laniakea. The Laniakea supercluster encompasses the Virgo supercluster and far more besides. It spans 520 million light-years and contains roughly 100,000 galaxies, all of them flowing toward the great attractor at its gravitational center. Laniakea is our true neighborhood, the gravitational basin in which we reside. And Laniakea is itself part of an even larger structure, the Pisces-Cetus supercluster complex. This is a galactic filament, one of the strands of the cosmic web, stretching approximately 1 billion light-years from end to end. 1 billion light-years. It is one of the largest coherent structures ever identified. A thread of galaxy clusters and superclusters, including Laniakea, strung along a single filament of the cosmic web. And all of this, the Pisces-Cetus supercluster complex, Laniakea, the Virgo supercluster, the local group, the Milky Way, the Sun, and the Earth, is itself a small fragment of the observable universe. The observable universe is a sphere centered on Earth with a diameter of approximately 93 billion light-years. It contains an estimated 2 trillion galaxies and 10 to the power of 24 stars. More stars than every grain of sand on every beach and every desert on this planet put together. The Pisces-Cetus supercluster complex, one of the largest coherent structures we know of, stretches 1 billion light-years. The observable universe is 93 billion light-years across. Our largest known structure is roughly 1% of the diameter of the observable universe. Think about that for a moment. The filament that holds our supercluster, that holds our galaxy cluster, that holds our galaxy, that holds our star, that holds our planet, is 1% of what we can see. We are small beyond comprehension. A speck within a thread, within a web, within a sphere so vast that light itself, traveling at 300,000 kilometers per second, requires 13.8 billion years to cross it. And 93 billion light-years sounds like everything. It sounds like the whole story. It sounds like the end of the road. It is not. 93 billion light-years is not the size of the universe. It is the size of the portion of the universe from which light has had time to reach us since the Big Bang. Beyond the edge of the observable universe, there is more. Vastly more. The observable universe may turn out to be a keyhole, a narrow window opening onto a room of incomprehensible size. To understand why, we need to understand what actually happens at the edge, what we see when we look out to the limit of what light can deliver to our eyes, and what lies beyond the last photon that will ever reach us. The edge of the observable universe is not a wall. It is not a boundary in space. It is a boundary in time, a boundary defined by the finite speed of light and the finite age of the cosmos. Approaching it will teach us something about the universe that is simultaneously beautiful and deeply unsettling. The observable universe is not merely a sphere of galaxies. It is also a cage of expanding space out of which no signal, no message, no spacecraft will ever escape. A cage that is somehow growing larger and smaller at the same time. Chapter 8. The Edge of Sight. Here is a misconception that almost everyone carries around without noticing. The universe is 13.8 billion years old. Therefore, the farthest we can see must be 13.8 billion light-years in every direction. It makes intuitive sense. Light travels at 1 light-year per year. The universe has existed for 13.8 billion years. So the light can only have made it 13.8 billion light-years. Simple. And wrong. The farthest we can see is not 13.8 billion light-years. It is roughly 46 billion light-years in every direction. The observable universe has a diameter of approximately 93 billion light-years. How is that possible when the universe is only 13.8 billion years old? Because space itself has been expanding throughout the entire journey. When a distant galaxy emitted the light we are now catching 13 billion years ago, that galaxy was much closer to our position than it is today. The light began its trip. But while it was in transit, the space between that galaxy and the eventual location of Earth was stretching. The galaxy was being carried farther and farther away by the expansion of the universe. By the time the light finally reaches our telescopes, the galaxy that emitted it is no longer 13 billion light-years away. It is now roughly 46 billion light-years away. It has been receding from us the entire time the light was crossing the gap. This is the difference between what astronomers call the light travel distance and the comoving distance. The light travel distance is how long the light has been in motion. At most 13.8 billion years. The comoving distance accounts for the expansion of the universe that took place during that travel time. In comoving terms, the edge of the observable universe is about 46.1 billion light-years away in every direction. That gives us a sphere 93 billion light-years across. At the very edge of this sphere, we do not see galaxies. We see something older, something more fundamental. We see the cosmic microwave background. The cosmic microwave background, or CMB, is the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, during an event called recombination. Before recombination, the universe was so hot and dense that electrons and protons could not combine to form atoms. Free electrons endlessly scattered photons, keeping the universe opaque. Light could not travel in a straight line for any real distance. It was trapped in a fog of superheated plasma. Then, as the universe expanded and cooled, the temperature dropped below roughly 3,000 Kelvin. Electrons were at last captured by protons, Neutral hydrogen atoms formed, and suddenly, the universe became transparent. The photons that had been bouncing around inside the plasma were released. They streamed outward in every direction. Those photons have been traveling ever since, cooling and stretching as the universe expanded, their wavelengths elongating from visible light into microwaves. In 1964, Arno Penzias and Robert Wilson at Bell Labs accidentally detected this radiation while trying to calibrate a microwave antenna. They found a faint, uniform hiss of microwave radiation coming from every direction in the sky. They could not get rid of it. It was not interference, it was not equipment noise. It was the echo of the Big Bang, the afterglow of creation. It earned them the Nobel Prize in Physics in 1978. The CMB is the farthest thing we can see with any form of light. It is a wall of radiation surrounding us in every direction, marking the precise moment when the universe first became transparent. Beyond it, in the era before recombination, the universe was opaque. No photon from that epoch can reach us. The CMB is the ultimate horizon for any observation made with light. Everything outside of it is invisible to every telescope ever built or ever imaginable that uses photons. There is one slight extension possible in theory. Neutrinos, those ghostly subatomic particles that barely interact with matter, would have decoupled from the primordial plasma earlier than photons. A cosmic neutrino background is thought to exist, carrying information from when the universe was only about 1 second old. If we could ever directly detect it, our view would push slightly further out, to a comoving distance of roughly 46.31 billion light-years. But directly detecting the cosmic neutrino background is far beyond our current technology. For now, the CMB is the wall. There is something even more confining than the CMB, something that defines the absolute limit of what we will ever be able to see, no matter how long we wait or how good our instruments become. It is called the cosmic event horizon. Because the expansion of the universe is accelerating, driven by dark energy, there are regions of space that are already receding from us faster than the speed of light. Right now, as you listen to this, galaxies beyond a certain distance are being carried away by the expansion of space at velocities that exceed 300,000 kilometers per second. This does not violate Einstein's theory of relativity. Relativity says that nothing can travel through space faster than light, but it places no limit at all on how fast space itself can expand. Space is not a thing moving through a medium. Space is the medium, and it can stretch as fast as it likes. Any light emitted by those distant galaxies right now will never reach us. The photons leave the galaxy and begin traveling toward us at the speed of light. But the space between us and them is expanding faster than the photons can cross it. The photons fall behind. They are running on a treadmill that accelerates under their feet. They will never arrive. This creates a boundary, the cosmic event horizon. Beyond it, no signal can reach us. No light, no radio wave, no gravitational wave, nothing. It is the ultimate prison wall, the edge of our causal universe. Everything past the cosmic event horizon is, and will forever be, totally disconnected from us. We cannot see it, we cannot communicate with it, we cannot interact with it in any way. There is a future visibility limit. Over time, light from regions just past our current view will gradually arrive, because those photons have been traveling toward us since before the expansion accelerated them beyond reach. This limit extends to objects currently about 61 billion light-years away. Over billions of years, our observable volume will roughly double. That is the maximum. The final view. After that, the accelerating expansion will ensure that no new light from beyond that boundary will ever arrive. And as the expansion continues to accelerate, galaxies that are currently visible will eventually cross the event horizon and disappear one by one over trillions of years. The galaxies outside our local gravitationally bound group will redshift into invisibility. Their light will stretch to wavelengths too long to detect. They will fade like ships sailing over the horizon of an ocean that is growing faster than they can return. In the far, far future, the only galaxies visible from our vantage point will be the few dozen that belong to our own local group, the ones gravitationally bound tightly enough to resist the expansion. To any civilization living in that distant era, the universe will appear to be a single galaxy floating in an infinite black void. They will have no way to know that trillions of other galaxies once filled the sky. No way to detect the cosmic microwave background, which will have redshifted to undetectable wavelengths. No way to deduce the Big Bang. Their cosmology will be wrong through no fault of their own, because the evidence will have been carried beyond their reach by the expansion of space. We live in a privileged moment right now. In this narrow window of cosmic history, we can still see the CMB. We can still detect distant galaxies. We can still stitch together the story of the Big Bang and the evolution of the universe. In the distant future, that will no longer be possible. The universe is slowly, inexorably hiding its own history. So this is our cage, 93 billion light-years across, bounded by the cosmic microwave background in one sense, and the cosmic event horizon in another. Everything we know, everything we have ever measured, everything our instruments can detect exists inside this sphere. And everything beyond it is a mystery. But here is the question that matters most. How big is everything out there beyond it? Is the unobservable universe slightly larger than what we can see? Or is it incomprehensibly, terrifyingly, absurdly larger? The answer depends on which physicist you ask, and some of the answers will make you feel smaller than anything in this documentary has so far. But before we go beyond the wall, we need to deal with what is happening on this side of it. Because the telescope that was supposed to confirm our understanding of the early universe has instead shattered it. And the crisis it has revealed is only getting worse. Chapter 9. What James Webb is really showing us. The James Webb Space Telescope launched on December 25, 2021. It was the most expensive, most complex, and most anticipated scientific instrument ever built. 25 years in development. $10 billion in cost. A 6.5-meter gold-plated mirror engineered to collect infrared light from the most remote reaches of the cosmos. It was stationed at the second Lagrange point, roughly 1.5 million kilometers from Earth, where it orbits the Sun in gravitational lockstep with our planet. It unfurled its sunshield, chilled its instruments to near absolute zero, and turned its golden eye toward the darkness. What it has found out there has shaken cosmology to its foundations. In January 2026, NASA announced the confirmed detection of the most distant galaxy ever observed, MOM-Z14. The name comes from the MIRAGE or Miracle Survey, a spectroscopic program designed to confirm high redshift galaxy candidates. The Z14 refers to the galaxy's approximate redshift. Spectroscopic analysis using Webb's near-infrared spectrograph confirmed a redshift of 14.44. That number means that light from MOM-Z14 has been traveling toward us for more than 13.5 billion years. We are seeing the galaxy as it existed only 280 million years after the Big Bang. When the universe was 2% of its current age, when the cosmos was still in its infancy, still emerging from the Dark Ages, the era before the first stars and galaxies ignited. And MOM-Z14 should not look the way it does. According to the models that were in place before Webb launched, galaxies at this cosmic epoch should be dim, small, simple collections of primordial gas just beginning to assemble their first stars. The universe was too young for anything elaborate. There had not been enough time for large-scale star formation, not enough time for heavy elements to accumulate, not enough time for galaxies to grow bright and structured. MOM-Z14 defies every one of those expectations. It is startlingly luminous, with an absolute ultraviolet magnitude of -20.2. It is extremely compact, just 74 parsecs in effective radius. That is roughly 240 light-years. For comparison, the distance from the Sun to the center of the Milky Way is about 26,000 light-years. This galaxy is tiny, but it is blazing. Its spectrum reveals elevated nitrogen emission. Nitrogen is an element that ordinarily requires multiple generations of stars to produce. Massive stars fuse hydrogen and helium in their cores, then explode as supernovae, scattering heavier elements into the surrounding gas. New stars form from that enriched gas and produce even heavier elements. Over many cycles, nitrogen builds up. But 280 million years is simply not enough time to run through many stellar generations. The presence of nitrogen in MOMZ14 suggests something unusual is happening. The research team proposed that supermassive stars, far more massive than anything in our nearby cosmic neighborhood, may have formed in the dense environment of the early cosmos and manufactured nitrogen through exotic nuclear processes far more rapidly than standard stellar evolution allows. And there is another anomaly. MOMZ14 appears to have partially ionized its own surroundings. The early universe was filled with neutral hydrogen gas, a thick fog that blocked ultraviolet light. The epoch of reionization is the period when the first stars and galaxies produced enough ultraviolet radiation to ionize this fog and make the universe transparent. Most models predict that at redshift 14, the universe should still be almost entirely neutral, close to 100% fog. But MOMZ14's surroundings show signs of partial ionization. This tiny galaxy, only 280 million years after the Big Bang, has already begun clearing the fog around it. Something the model said should not be possible at this epoch. Rohan Naidu, the lead author and astrophysicist at MIT's Kavli Institute for Astrophysics and Space Research, said it bluntly. He said that with Webb, we are peering farther into the past than any humans have before us. And what we are seeing looks nothing like what we predicted, which is both challenging and thrilling at the same time. MOMZ14 is not an isolated anomaly. It is the most extreme example of a pattern that has been building since Webb began making observations. The telescope has identified over 100 bright galaxies at redshifts above 10, in an era where the pre-launch consensus models predicted essentially none. The number density of bright galaxies at redshift 14 to 15 is more than 100 times higher than what those models expected. 100 times. Not 10% more. Not double. 100 times. Among the most striking discoveries is Xulong, a galaxy identified by an international team and published in Astronomy and Astrophysics in 2025. Xulong sits at a redshift of approximately 5.2, meaning we see it as it was roughly 1 billion years after the Big Bang. That is about 700 million years older than MOMZ14. But what makes Xulong extraordinary is its maturity. It is an ultra-massive grand design spiral galaxy. It has full spiral arms, a mature central bulge, a total stellar mass of roughly 100 billion suns. It looks like a galaxy that has had billions of years to evolve. It had 1 billion. Galaxies like Xulong are not supposed to exist that early. Spiral structure requires dynamical settling. Central bulges require repeated mergers and sustained gas accretion over long periods of cosmic time. Assembling 100 billion solar masses of stars in only 1 billion years strains the physical limits of what star formation can achieve. And yet, there it is. Fully formed, beautiful, impossible. Jacob Shen, the postdoctoral researcher at MIT who works on the MOMZ14 team, captured the mood of the entire field when he said there is a widening chasm between theory and observation in the early universe, presenting compelling questions that will have to be addressed going forward. A widening chasm, that is diplomatic language for something more alarming. The standard model of cosmology, lambda CDM, is being challenged at its foundations, not by fringe theories, not by speculative philosophy, by data, by the most powerful telescope ever built, doing exactly what it was designed to do, looking at the early universe, reporting what it sees. To be clear, the Big Bang itself is not in question. The evidence for the Big Bang is overwhelming and comes from multiple independent sources: the cosmic microwave background, the observed expansion of the universe, the observed abundances of the light elements, hydrogen, helium, and lithium, which match the predictions of Big Bang nucleosynthesis almost exactly. These pillars are standing firm. What is breaking is the timeline. The sequence of events that lambda CDM predicts should follow the Big Bang. According to the model, galaxies should form slowly, growing through mergers and gradual gas accretion over billions of years. Small galaxies should form first, then merge into larger ones. Bright, massive, structured galaxies should not appear until the universe is well into its adolescence, at minimum several billion years old. James Webb is showing us something different. Galaxies are forming faster than the models allow. They are brighter than they should be. More massive, more chemically enriched, more structured. They look old when they should look young. Proposed solutions are multiplying. Some researchers suggest that star formation in the early universe was far more efficient than models assumed. Perhaps the conditions inside the dense early cosmos allowed gas to collapse into stars at rates that vastly exceeded anything in the modern universe. Others invoke early dark energy, a hypothetical phase of extra-dark energy that existed briefly in the first few 100 million years, accelerating the growth of structures. Others suggest modifications to the physics of dark matter, perhaps allowing it to interact with itself in ways that enhanced gravitational collapse in the early universe. Some have even proposed entirely new particle physics. None of these solutions fully works. None of them can explain all the anomalies without creating fresh problems. The Tensions in Cosmology 2025 conference held in Corfu, Greece, brought together over 130 researchers to address the growing list of discrepancies. The conference report, published in Nature Astronomy in 2026, made clear that the field is at a turning point. This is not a minor correction to an otherwise healthy model. This could require new fundamental physics. And the crisis does not stop at early galaxies. It connects directly to the problem we opened with in Chapter 1, the Hubble tension, the expansion rate that does not match, the model that keeps predicting one number while the universe keeps delivering another. These are not separate problems. They are symptoms of the same condition. The lambda CDM model, the standard model of cosmology that has governed our picture of the universe for a quarter century, may be failing. And if it fails, everything built on top of it, our estimates for the age of the universe, the size of the universe, the fate of the universe, all of it comes into question. The Hubble tension is the crack in the wall, and every new measurement is making it wider. Chapter 10. The Hubble crisis. 2 numbers. That is all it takes to throw the entire field of cosmology into crisis. 2 numbers that should agree with each other and stubbornly do not. The first number comes from the cosmic microwave background, the afterglow of the Big Bang, mapped in exquisite detail by the European Space Agency's Planck satellite from 2009 to 2013. Using the patterns imprinted on the CMB, combined with the standard lambda CDM model, cosmologists calculated the expansion rate of the universe. They arrived at a value of approximately 67.5 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. So for every 3.26 million light-years of distance between any 2 points in the universe, the space between them is expanding at 67.5 kilometers per second. The Atacama Cosmology Telescope, a ground-based radio telescope in the Chilean Andes, refined this measurement further. By combining CMB data with galaxy clustering and stellar age information, they arrived at a value of around 68.22, slightly higher than Planck but consistent with it. The early universe route was solid, approximately 67 to 68. The second number comes from the local universe. Instead of looking at the earliest light in the cosmos and working forward with a model, astronomers measured distances and velocities directly using the cosmic distance ladder. The distance ladder is a chain of techniques, each calibrated against the one below it. The first rung uses geometric methods known as parallax to measure distances to nearby stars. The second rung uses those nearby stars to calibrate the brightness of Cepheid variable stars, pulsating stars whose intrinsic brightness is directly related to their pulsation period. Measure the period. Calculate the true brightness, compare it to the observed brightness, get the distance. The third rung uses Cepheids in more distant galaxies to calibrate even more distant indicators, like type Ia supernovae. Each rung extends the reach of the last, building a bridge from our solar neighborhood out to galaxies billions of light-years away. Using this ladder, the SH0ES team, led by Nobel laureate Adam Rice of Johns Hopkins University, has consistently measured the Hubble constant at approximately 73 kilometers per second per megaparsec. Other teams, using independent methods, have returned similar numbers. The tip of the red giant branch method, which uses a different type of star to calibrate distances, gives values in the range of 69 to 72. Surface brightness fluctuation measurements give about 73.8. And in 2025, Daniel Skolnick of Duke University published a new measurement in the Astrophysical Journal Letters that pushed the local value even higher. His team used the COMA cluster, one of the most thoroughly studied galaxy clusters in the sky, as a calibration point. The Coma cluster is in our cosmic backyard. Its distance has been measured repeatedly by multiple independent methods over decades. Using this high-precision measurement as their first rung, combined with data from the Dark Energy Spectroscopic Instrument, they arrived at a Hubble constant of 76.5 kilometers per second per megaparsec. 67 from the early universe, 76 from the local universe. The gap is not closing, it is widening. For years, skeptics suggested that the discrepancy might be due to measurement error. Perhaps the Cepheid observations were contaminated by dust. Perhaps crowded star fields were making the measurements unreliable. Perhaps the calibrations were subtly wrong. In 2024 and 2025, the SH0ES team used the James Webb Space Telescope to re-observe the same Cepheid variable stars that had anchored their measurements. Webb's infrared capabilities provided sharper, cleaner images than the Hubble Space Telescope could achieve. The result was unambiguous. The Hubble data was correct. The Cepheids were exactly where and how bright the earlier measurements had claimed. Dust and crowding were not the problem. The local measurement of approximately 73 was robust. Then, in December 2025, the TD-COSMO collaboration published results from a completely independent method, time delay cosmography. This technique uses gravitationally lensed quasars. When a massive galaxy sits between us and a distant quasar, the galaxy's gravity bends the quasar's light, creating multiple images of the same object. Because each light path has a slightly different length, the images arrive at slightly different times. By measuring these time delays and modeling the mass distribution of the lensing galaxy, astronomers can calculate the Hubble constant directly. No Cepheids, no supernovae, no distance ladder at all. Their result matched the local measurements, not the CMB value. Every new independent method that measures the expansion rate of the local universe comes back with the same answer. And it is the wrong answer according to Lambda CDM. As of late 2025, the discrepancy has reached 5 sigma. In physics, 5 sigma is the gold standard for a genuinely real result. It is the same threshold used to claim the discovery of the Higgs boson at CERN in 2012. A 5 sigma result means that the probability the discrepancy is due to random chance is less than 1 in 3.5 million. This is not a fluke. This is not noise. This is something real. Skolnick said it directly. This is saying, to some respect, that our model of cosmology might be broken. He added that we are at a point where we are pressing really hard against the models we have been using for 2.5 decades, and we are seeing that things are not matching up. So what could fix it? What could explain why the universe appears to be expanding faster locally than the early universe data predicts? Several ideas are on the table. Early dark energy is one of the leading proposals. The idea is that a brief burst of additional dark energy existed in the universe before recombination, before the CMB was released. This extra energy would have altered the size of the sound horizon, the characteristic scale imprinted in the CMB, which in turn would change the Hubble constant derived from that data. In effect, the CMB value would shift upward, potentially matching the local measurements. But early dark energy models struggle to fit all the CMB data simultaneously. They fix one problem and create others. New neutrino physics is another proposal. If there are more species of neutrinos than the 3 we already know about, or if neutrinos have unexpected properties, this could alter the expansion history in the right direction. Modified gravity theories, which adjust Einstein's general relativity at cosmological scales, have also been explored. In 2025, a team led by Karsten Jadamczyk published a paper in Nature Astronomy proposing a different culprit: primordial magnetic fields. Tiny magnetic fields that may have existed from the earliest moments of the universe. Using supercomputer simulations at Simon Fraser University, the team showed that these fields could have accelerated the recombination process, changing the patterns in the CMB in ways that would shift the derived Hubble constant. If primordial magnetic fields existed, the CMB value of 67 might actually be an underestimate. The true value could be higher, closer to the local measurements. Levon Pogosian, a co-author and professor at Simon Fraser University, said that this could address 2 major unsolved puzzles simultaneously: the Hubble tension and the origin of cosmic magnetic fields. And then there is the void hypothesis, the possibility we encountered back in Chapter 3. If the Milky Way sits near the center of the KBC void, a region of below-average density roughly 2 billion light-years across, then the local expansion rate would naturally appear higher than the cosmic average. Galaxies inside a void are pulled outward by the denser surrounding regions, amplifying the local expansion. We would not need new physics at all. We would just need to accept that our address in the cosmos is slightly unusual. None of these solutions has been confirmed. None has been universally accepted. The Lambda CDM model, which has been the bedrock of cosmology for 25 years, has survived every challenge until now. It may still survive this one. Perhaps a combination of small effects will close the gap. Perhaps a subtle systematic error lurks in one of the measurement chains that no one has yet unearthed. Or perhaps the model is genuinely breaking. Perhaps the universe is trying to tell us something we do not yet know how to hear, that the physics we have used to build our picture of reality is incomplete, that something new, something fundamental, something we have not yet imagined is needed to properly understand how the universe actually works. And if our model of the universe is wrong about how fast it is expanding, it might also be wrong about how large it truly is. The observable universe of 93 billion light-years is calculated using Lambda CDM. If the model changes, the number changes. And beyond the observable universe, beyond the edge of sight, the estimates for the true size of the cosmos are not just large. They are staggering. Chapter 11. Beyond the Wall. The observable universe is 93 billion light-years across. That is a sphere containing 2 trillion galaxies, 10 to the power of 24 stars, and more planets than we can begin to count. It is everything we have ever seen, everything we have ever measured, everything that light has had time to deliver to our instruments since the universe was born. It is a fraction, a tiny, almost insignificant fraction of what actually exists. We know this because of one specific measurement, one deceptively simple property of the universe that has been confirmed to extraordinary precision. The universe is flat. In cosmology, flatness does not mean the universe is shaped like a table. It refers to the geometry of space itself. In a flat universe, the angles of a triangle add up to 180 degrees. Parallel lines remain parallel forever. Space does not curve back on itself. In a positively curved universe, like the surface of a sphere, the angles of a triangle add up to more than 180 degrees, and parallel lines eventually converge. The universe would be finite, but unbounded, like a balloon. You could travel in a straight line and eventually return to your starting point. In a negatively curved universe, like the surface of a saddle, the angles add up to less than 180 degrees, and parallel lines diverge. Measurements from the cosmic microwave background and from baryon acoustic oscillations, the fossilized sound waves of the early universe imprinted on the distribution of galaxies, tell us that the universe is flat to within 0.4%, 99.6% flat. The curvature, if it exists at all, is so slight that within the entire observable universe, space is indistinguishable from perfectly flat. And this has a staggering implication. If the universe were strongly curved, it could be small. A positively curved universe, like the surface of a sphere, could be finite and not much larger than the observable volume. But the flatter the universe is, the larger it has to be. Because the only way for our 93 billion light-year observable patch to appear perfectly flat is for the total universe to be vastly, overwhelmingly larger. In the same way that a basketball court looks flat to an ant, because the curvature of the Earth is too gentle to detect at that scale. A team of researchers at Oxford University analyzed the curvature constraints from the CMB and concluded that the universe is at least 250 times larger than the observable portion. At minimum, the full universe would be at least 23 trillion light-years in diameter. Its volume would be more than 15 million times what we can see. Let that settle. Everything we have discussed in this entire journey, every galaxy, every void, every filament of the cosmic web, every supercluster, every measurement ever made by every telescope ever built, all of it fits inside a volume that is at best 15 millionth of the whole. And that is the conservative estimate. Alan Guth, the physicist who proposed the theory of cosmic inflation in 1980, has estimated the size of the universe based on inflationary models. His numbers are not gentle. Cosmic inflation is the theory that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. In an inconceivably brief instant, the universe expanded by a factor of at least 10 to the power of 26. A region smaller than a proton ballooned into a volume larger than the observable universe today. This inflationary burst smoothed out the universe, flattened its geometry, and set the stage for all the structures we see. If inflation happened, and the evidence strongly suggests that it did, then the total universe is not just 250 times larger than the observable portion. It could be 10 to the power of 23 times larger. That is a 1 followed by 23 zeros, 100 sextillion times the observable universe. To make that number feel like something, consider this analogy. If you shrank the observable universe down to the size of a €1 coin, the full universe under Guth's estimate would be a sphere 250,000 light-years in diameter. That is more than twice the diameter of the Milky Way galaxy. The observable universe, 93 billion light-years across and containing 2 trillion galaxies, would fit on a coin. And the full universe would be larger than the galaxy we live in. And that is only one model. Some inflationary scenarios suggest that the universe is literally infinite. Not just very large, not just incomprehensibly large, actually infinite, extending forever in every direction with no boundary, no edge, no center. If the universe is infinite, then every possible arrangement of matter, every possible configuration of atoms, every possible history occurs somewhere. There would be other regions of space, so far away that light from them will never reach us, where the atoms have arranged themselves into an exact copy of Earth, with an exact copy of you, listening to an exact copy of this sentence, not as metaphor, as mathematical certainty. In an infinite universe with finite possible configurations of matter, repetition is not simply possible, it is guaranteed. That thought is either exhilarating or vertigo-inducing, depending on your temperament. But regardless of whether the universe is 250 times larger, or 10 to the 23 times larger, or infinite, one fact is clear. We will never see most of it. The cosmic event horizon seals us in. The accelerating expansion of space ensures that the vast majority of the universe is, and always will be, beyond our reach. Light from those distant regions will never arrive. Signals from any civilization that might exist there will never be received. We are isolated, confined to our observable bubble, a tiny luminous fishbowl floating in an ocean of unknowable immensity. Over time, our view will expand slightly. The future visibility limit extends to objects currently about 61 billion light-years away. This will roughly double the volume we can see. But even that doubled volume is a rounding error when set beside the whole. We will see twice as much and still see almost nothing. The universe is not just bigger than we thought, it is bigger than we can think. It exceeds not only our instruments but also our capacity for comprehension. Our brains evolved to navigate African savannas, to track prey across distances of a few kilometers, to memorize the locations of water and shelter. We did not evolve to grasp 10 to the 23. We did not evolve to feel what infinity means. We can write the equations, we can calculate the estimates, but we cannot experience the scale. And yet the equations point somewhere. The models, the mathematics, the logical extension of inflation all point toward the same unsettling conclusion. If inflation happened once, it probably did not happen just once. The same physics that inflated our universe may be inflating others. Right now, in regions of space so far beyond our horizon that the word distance loses its meaning. The universe we see may not be the universe. It may be a universe. One bubble in an infinite sea of bubbles, each with its own Big Bang, its own expansion, its own physics, its own stars and galaxies and voids. And maybe, just maybe, its own observers looking up at their own night sky and wondering if they are alone. Chapter 12. The Multiverse. If cosmic inflation happened, and the evidence from the cosmic microwave background, the flatness of space, and the uniformity of the universe on large scales all suggest that it did, then most models of inflation predict something extraordinary. They predict that inflation does not stop everywhere at once. Inflation is not a one-time event. It is a process, a runaway expansion of space driven by the energy of a quantum field. In our region of space, inflation eventually ended. The energy of the inflaton field decayed. The expansion slowed. Matter formed. Galaxies emerged. Stars ignited. Life arose. But in other regions of space, farther away than any photon could ever reach, inflation may still be going. Right now, the quantum field that drove the expansion in our neighborhood may still be driving expansion in others. This idea was formalized in the early 1980s by physicists including Paul Steinhardt and Alexander Vilenkin, and further developed by Alan Guth. They called it eternal inflation. In this framework, our Big Bang was not the beginning of everything, it was a local event. One pocket of space where inflation happened to stop, where the energy of the inflaton field happened to decay, where conditions happened to be right for particles and forces, and eventually galaxies and planets and life. But outside our pocket, inflation continues, and it continues forever. Because inflation is exponential. The inflating regions of space expand faster than the pockets where inflation ends. Even as bubble universes like ours form and begin their own slow expansion, the space between them inflates faster, creating room for more bubbles, more pocket universes, each with its own Big Bang, its own initial conditions, its own history. The result is a multiverse, not in the science fiction sense, not parallel dimensions accessed through portals or mirrors. A multiverse in the most literal physical sense, an infinite collection of causally disconnected pocket universes, each one expanding and evolving independently, each one inaccessible to every other. No signal can pass between them, no light, no gravity, no information of any kind. They are islands in an ever-expanding sea of inflating space. And here is where it becomes genuinely strange. In some versions of the multiverse, particularly those derived from string theory, the physical constants that govern our universe are not fundamental. They are contingent. String theory, the leading candidate for a unified theory of physics, predicts an enormous number of possible vacuum states. Each vacuum state corresponds to a different set of physical laws, different strengths of gravity, different masses for particles, different numbers of spatial dimensions. The total number of possible configurations is estimated at 10 to the power of 500, a number so large that writing it out would require more digits than there are atoms in the observable universe. In the string landscape version of the multiverse, each bubble universe could settle into a different vacuum state, a different set of physical laws. Some universes might have a strong nuclear force so weak that atoms cannot form. Some might have a cosmological constant so large that space tears itself apart before galaxies can coalesce. Some might have no stable matter at all, just a formless sea of radiation expanding into nothing. Others might have conditions similar to ours, with stars and planets and the potential for chemistry and complexity in life. The laws of physics we observe, the specific values of the gravitational constant, the speed of light, the mass of the electron, the strength of electromagnetism, may not be the laws of the universe. They may only be the laws of our universe, local conditions, one throw of an infinite cosmic dice. And we exist in this particular throw not because it is special, but because it is the kind of throw that allows observers to exist at all. This reasoning is called the anthropic principle. We see the universe we see because it is the kind of universe capable of producing beings capable of seeing. Whether the multiverse is a prediction, a philosophical proposition, or something in between is one of the most contentious questions in modern physics. Critics argue that a theory which predicts everything predicts nothing. If any set of physical laws is possible in some pocket universe, then nothing is falsifiable. The multiverse becomes a framework that can explain any observation by pointing to a different bubble where that observation would occur. This, the critics say, is not science. It is metaphysics. Proponents push back. They argue that eternal inflation is not a speculative add-on to physics. It is a natural, almost unavoidable consequence of the same inflationary theory that has been confirmed by CMB observations. If you accept inflation, and most cosmologists do, then eternal inflation follows from the mathematics. You do not get to keep the part of the theory you like and discard the part that makes you uncomfortable. And there are hints, faint, tantalizing, far from conclusive, that the multiverse might leave fingerprints. If two bubble universes happen to nucleate close enough in the inflating space, they could collide. A bubble collision would leave a specific pattern in the CMB, a circular bruise of slightly different temperature in the microwave background. Some researchers have claimed to identify anomalous features in the CMB data that could be consistent with a bubble collision. Cold spots, asymmetries, patterns that do not fit the simplest lambda CDM predictions. These claims are heavily debated. The statistical significance is below threshold. But they exist. They hover at the edge of the data like shadows at the periphery of vision. In 2018, shortly before his death, Stephen Hawking CO authored a paper with Thomas Hertog proposing a way to reduce the multiverse from an infinite ensemble to something finite and potentially testable. Using the holographic principle, a concept from string theory that suggests the physics of a volume of space can be described by a theory on its boundary, Hawking and Hertog argued that eternal inflation could be described by a finite set of possible histories. This would make the multiverse, in principle, subject to observational constraints. Gravitational wave astronomy, they suggested, might eventually provide the data needed to test these ideas. The multiverse remains at the boundary between science and philosophy. It is the most extreme logical extension of the physics we trust. It cannot be confirmed by any observation currently conceivable, but it cannot be ruled out either. It is the ultimate expression of the theme that has run through this entire journey. The universe is larger than we thought. Not simply larger. Larger in a way that defies intuition, experience, and in some formulations even the very concept of size. If the multiverse is real, our universe is one island in an infinite archipelago. Each island has its own ocean, its own weather, its own geology. Some are habitable. Most are not. We are on one of the habitable ones. Marveling at the sky, wondering whether the ocean has a far shore. It may not. The ocean may be infinite. But even within our single island, within our one observable universe, within this 93 billion light-year bubble of light and matter and dark energy, the question that haunts us most is not about physics. It is not about expansion rates or vacuum states or bubble collisions. It is simpler than that, more ancient than that. It is the question every civilization has eventually asked. In all of this vastness, in all of these trillions of galaxies and billions of trillions of stars and countless planets and countless habitable zones, is there anyone else? Is anything out there looking back? Or are we alone? Completely, utterly, cosmically alone. Staring into the dark, waiting for an answer that never comes. Chapter 13. Are we alone? Let us talk about the numbers. Because the numbers are overwhelming. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains, on average, between 100 billion and 400 billion stars. The total number of stars in the observable universe is estimated at 10 to the power of 24, 1 septillion, a 1 followed by 24 zeros. Most of those stars have planets. Data from the Kepler Space Telescope and from ground-based surveys suggest that the average star in the Milky Way hosts at least 1 planet. Many stars host multiple planets. Current estimates suggest that there may be more planets than stars in our galaxy alone. In the Milky Way, conservative estimates put the number of rocky planets in the habitable zone, the orbital range where liquid water could exist on a planet's surface, at somewhere between 300 million and 10 billion. Scale that up. If there are 300 million habitable zone rocky planets in the Milky Way, and 2 trillion galaxies in the observable universe, the total number of potentially habitable worlds is in the billions of trillions. And if the universe is 250 times larger than the observable portion, or 10 to the 23 times larger or infinite, then the number of potentially habitable worlds is beyond any meaningful estimate. The probability that Earth is the only planet in all of that where life arose is not just small, it is absurd. Unless there is something about life we fundamentally do not understand. Unless the leap from chemistry to biology is so improbable that even with billions of trillions of chances, it has happened only once. We do not know the probability of abiogenesis, the emergence of life from non-living chemistry. It could be common, it could be vanishingly rare. We have a sample size of 1, Earth, and from that single data point, we cannot draw conclusions. Life could be everywhere, or we could be alone. Both are consistent with the evidence. But if life is not rare, then the silence is deafening. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to the question of extraterrestrial life. Fermi, known for his ability to work out back-of-the-envelope calculations with remarkable speed, considered the age of the galaxy, the number of stars, the likelihood of planets, and the time it would take a technologically capable civilization to colonize the galaxy, even at modest speeds. His conclusion was simple and devastating. If intelligent life is common, the galaxy should be teeming with it by now. Civilizations have had billions of years to spread. Even at speeds far below the speed of light, a single civilization could colonize the entire Milky Way in a few tens of millions of years. A blink in cosmic time. And yet, there is no evidence that anyone has done so. No confirmed signal. No visitation, no artifact, no megastructure visible in our telescopes. Nothing. Where is everybody? That question became known as the Fermi paradox. And in the decades since Fermi asked it, the paradox has only deepened. Our telescopes have grown more powerful. Our surveys have expanded. We have listened for radio signals with projects like the Search for Extraterrestrial Intelligence, SETI. We have scanned the skies for laser pulses, infrared signatures, technosignatures of every kind. We have found nothing. The explanations for the silence are numerous, and each one is unsettling in its own way. The Great Filter hypothesis suggests that somewhere between dead chemistry and a galaxy-spanning civilization, there is a barrier, a step so difficult that almost no one gets past it. The question is whether the filter is behind us or ahead of us. If the filter is behind us, if the hard step was the origin of life, or the development of complex cells, or the evolution of intelligence, then we are among the lucky few who made it through. And the universe is full of microbial worlds that never took the next step. If the filter is ahead of us, if civilizations commonly arise but invariably destroy themselves through war, environmental collapse, or technological catastrophe before becoming interstellar, then our future is grim. The zoo hypothesis proposes that advanced civilizations exist but deliberately avoid contact with us. They are watching, but they are not interfering. The dark forest theory, popularized by the science fiction author Liu Cixin, suggests that advanced civilizations stay silent because the universe is dangerous. Any civilization that reveals itself risks destruction by others. The safest strategy is to remain hidden, to treat the cosmos as a dark forest in which every rustling bush might be a predator. And then, there is the simplest explanation of all: distance. Everything we have discussed in this journey has been building toward this realization. The universe is not simply big, it is structured to isolate. The cosmic web separates galaxies along filaments that span hundreds of millions of light-years. The voids between the filaments are chasms of emptiness. The expansion of space is accelerating, pushing galaxy clusters apart faster and faster. The cosmic event horizon seals off most of the universe permanently. Even within the Milky Way, the distances are paralyzing. The nearest star is 4.24 light-years away. At Voyager 1 speed, 73,000 years away, a radio signal sent today would take 4 years to arrive. A response would take another 4, and Proxima Centauri is the nearest star. The galaxy is 100,000 light-years across. A signal sent from one side to the other would take 100,000 years to arrive. Civilizations could rise and fall in the time it takes their first message to reach the far side of the galaxy. And our radio signals, our electromagnetic calling card, our only evidence that we exist, have traveled just 125 light-years. A sphere 125 light-years in radius inside a galaxy 100,000 light-years wide. It is a whisper inside a cathedral. And beyond the Milky Way, the distances become so absurd that the question shifts from, will we find anyone, to, could we ever know if anyone is there? The Andromeda galaxy is 2.5 million light-years away. The nearest large galaxy cluster, the Virgo cluster, is 54 million light-years away. A message sent there today would arrive 54 million years from now. The sender species would almost certainly be long extinct before the response came back. Communication across the cosmic web is not merely difficult. It is functionally impossible on any timescale relevant to a biological civilization. This may be the answer to the Fermi paradox. Not that intelligent life is rare, not that civilizations destroy themselves, not that they are hiding, but that the universe is too large. The distances are too great. The cosmic architecture itself is a quarantine. Every civilization is an island surrounded by an ocean of space so vast that no message, no ship, no signal can bridge it in any meaningful sense. We are not alone because life is impossible elsewhere. We are alone because togetherness is impossible across these distances. The universe may be full of voices, all of them calling out, all of them unheard. The question is not simply, are we alone? The question is, could we ever know? And maybe, in the end, the answer is no. Maybe, the universe is built in such a way that its inhabitants are forever isolated, forever wondering, forever looking up at the same stars and asking the same question, and never receiving an answer. Maybe the silence is not a mystery to be solved. Maybe it is a feature. A fundamental property of a cosmos too large for any of its children to find each other. That is a lonely thought. But it is not the last thought. Because there is another way to look at all of this, another way to interpret our smallness, our silence, our isolation, a way that does not end in despair, a way that ends in something like wonder. Chapter 14. The Pale Blue Dot Revisited. On February 14, 1990, the Voyager 1 spacecraft was 6 billion kilometers from Earth. It had completed its planetary mission. The cameras were about to be shut down permanently. Carl Sagan, the astronomer and author who had championed the Voyager program from its beginning, made a request to NASA. Turn the camera around, take one last photograph. Not of a planet, not of a moon, of home. NASA agreed. Voyager 1 rotated its camera and pointed back toward the inner solar system. The resulting image showed Earth as a tiny speck, a pale blue dot less than a single pixel wide, caught in a scattered beam of sunlight, barely visible against the vastness of space. Sagan looked at that image and wrote words that have echoed through the decades since. He described how everything we have ever known, every human being who has ever lived, every king and peasant, every saint and sinner, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every politician, every superstar, every leader, every hero and coward lived out their lives on that mote of dust suspended in a sunbeam. That photograph was taken from 6 billion kilometers away, barely outside the solar system, a distance that in cosmic terms is nothing. It is not even a rounding error. It is not even the first step on the staircase that leads to interstellar space, let alone to the edge of the galaxy, let alone to the edge of the observable universe. And already, from that trivial distance, Earth was invisible. Now consider what we have learned tonight. The observable universe is 93 billion light-years across. The Milky Way, our galaxy, is 100,000 light-years across and contains 250 billion stars. Earth orbits one of those stars, an unremarkable yellow dwarf in a minor spiral arm. Our radio signals have traveled 125 light-years, a tiny bubble inside a galaxy that does not know we are here. The Milky Way is one of 100 galaxies in the local group. The local group is a speck within the Virgo supercluster. The Virgo supercluster is a lobe of Laniakea. Laniakea is one structure on the Pisces-Cetus supercluster complex, and that filament is roughly 1% of the observable universe. The observable universe itself may be 1/15,000,000th of the full universe, or less, or infinitely less. It may be one bubble in an infinite multiverse. Each bubble with its own physics, its own stars, its own empty voids. We are nothing. By every measure of size, scale, distance, and time, we are nothing. A virus on a grain of sand in a desert that stretches forever. And yet, We are here, and we know all of this. That is the paradox. That is the miracle, if you want to call it that. The universe is 13.8 billion years old. For most of that time, it was a hot fog. Then a cooling darkness. Then a slow gathering of matter into stars and galaxies and planets. For billions of years, there was no one to see it. The cosmic web wove itself in silence. The voids expanded without witnesses. The filaments glowed, and no one observed the glow. That on one small rocky planet, orbiting one small star, on one thin filament of the web, something happened. Atoms that had been forged in the cores of stars, scattered by supernova explosions, gathered by gravity, and organized by chemistry, crossed a threshold. They became aware. They looked up. They asked questions. Every atom in your body was made in a star. The iron in your blood was forged in a supernova. The calcium in your bones was assembled in the last moments of a dying star, more massive than the sun. The hydrogen in the water that fills your cells has been around since the first minutes after the Big Bang. You are not separate from the universe. You are the universe. A specific arrangement of the universe's matter that has developed the capacity to contemplate itself. Hydrogen, given 13.8 billion years, became a thing that could wonder about hydrogen. That is not insignificance. That is the most extraordinary thing that has ever happened. The universe did not just produce matter. It did not just produce stars. It did not just produce galaxies. It produced observers. Beings capable of measuring 93 billion light-years of reality from a planet 12,742 kilometers in diameter. Beings capable of detecting the afterglow of the Big Bang. Of photographing a single strand of the cosmic web 3 million light-years long. Of identifying a galaxy 280 million years after the beginning of time. Of calculating that 95% of reality is composed of things they cannot see. We are small. Impossibly small. But we are the part of the universe that knows how small it is, and that knowing is not nothing. That knowing is extraordinary. Carl Sagan understood this. His pale blue dot speech was not a lament. It was a call. He was not saying that we are meaningless because we are small. He was saying that our smallness demands that we treat this place, this moment, this speck, with care. Because it is all we have. Because there is no evidence that anyone else is coming to save us. Because the vastness of the cosmos does not make our lives less precious. It makes them more precious, concentrated, rare, possibly unique. The universe is under no obligation to make sense to you. It is under no obligation to be the size you would prefer. It is under no obligation to contain neighbors you can visit or signals you can detect. It simply is vast, mostly empty, mostly dark, mostly unknown. But you exist anyway. Against overwhelming odds, against the indifference of entropy, and the emptiness of the voids, and the silence of the sky, you exist on a filament of the cosmic web, in a void within a void, circling a star that will someday die, on a planet that will someday be swallowed by that dying star, in a galaxy that will someday merge with Andromeda, in a universe that is slowly going dark. And right now, in this brief moment, in this narrow window of cosmic history, where the CMB is still detectable, and the distant galaxies are still visible, and the story of the universe can still be pieced together, you are here, listening, thinking, wondering. The universe has been around for 13.8 billion years. Human civilization has existed for roughly 5,000. You have been alive for a handful of decades. The window during which you exist, the sliver of time during which your atoms are arranged in a way that can experience and contemplate and feel, is so thin that it should not register on any cosmic scale. And yet it does. Because you are the universe's way of experiencing itself. You are not a bystander. You are the cosmos, briefly aware. Every measurement we have discussed tonight, every number, every light year, every billion, was calculated by beings made of stardust, using instruments built on a pale blue dot. That is not a footnote to the story of the universe. That is the climax. That is the point. The universe spent 13.8 billion years building something that could look at it and say, I see you, I measure you, I understand you, and I am so very, very small. Maybe that is the point. Maybe the universe does not need to be understood by something large. Maybe understanding is its own scale. Maybe consciousness, awareness, the simple act of looking up and feeling awe is the largest thing in the cosmos. Not in meters, not in light years, in meaning. The Boot's void is 330 million light years of almost nothing. But it has never known it is empty. You do. The cosmic web stretches across the entire observable universe. But it has never seen itself. You have. The multiverse, if it exists, contains infinite possibilities. But none of them matter unless something somewhere is aware of them. You are that awareness. Fragile, temporary, impossibly rare, but real. The universe is not empty. It just feels that way because we are small, and space is vast, and the light takes so long to travel. But somewhere, on a thin filament of the cosmic web, in a void called the local hole, circling an ordinary star, on a planet that still has blue oceans and green forests and people who look up at the night sky and wonder, the universe is looking at itself, and wondering what it means. If you enjoyed this deep exploration of the cosmos and what it means to be part of it, please like this video and subscribe to the channel. Tell us in the comments what surprised you most about the true size of the universe and what we should explore next. These are not only questions for scientists, they are questions for all of us. Because the universe is not something out there, it is something we are part of. And every question we ask about it is a question we are asking about ourselves. Thank you for spending this time with us. We will see you in the next journey.